So one lesson that really resonated with me was the conservation of of energy. And I really like this one because of the lab that we did with the skateboarding because one of my favorite hobbies is skateboarding. And something I've always thought of, like, whenever I skateboarded, I'm always at the top of the skate ramp whenever I'm about to drop in. And I'm just completely still, and then out of nowhere, all I do is just drop in, and I gain a crazy amount of momentum and speed. And that really, like, had me wondering. And whenever I like ride the other side of the ramp, I don't get as high as or I get up there, and then I slow down, and then until I'm about to stop, I start rolling back down again. And I was just like, I never knew where that speed was coming from because I'm not using my foot to like move myself. Obviously, that's all just from dropping in from up the hill. And if energy like can't be created, why am I so much faster at the bottom than I am at the top where I start stopping? Um, but anyways, the conservation of energy law, it just explains how like roller coasters and like skiing and skateboarding and pendulums. I always love pendulums. How they just work in general. And I think that once you understand this concept, you start to see it everywhere. And once I understood it, I started to see it everywhere. But what is the conservation of energy? See, the law of conservation of energy tells us that energy can't be created or destroyed. It can only be transferred from one thing or say one object to another, and like it changes forms, right? From one form to another. So the total amount of energy in the system stays the same, um, unless it leaves due to like air resistance or like friction. Let's just say in real life scenarios. But the first energy would be potential energy. Well, gravitational potential energy. I'll just put a G there. But the potential energy is just it's just stored energy, you know? And skateboarding, it's like the energy that I have just because I'm high above the ground. Like because I'm that high, I have the potential energy in the system. And the equation that we use to represent this is PE equals mgh, where PE is the potential energy measured in the SI units of joules. M is the mass measured in the SI units as kilograms. G is the gravity, which is 9.8. Let me see, 9.8 meters per second squared, that's the SI units. And H would be height in the situation. We measure that using meters. That's the SI units. It's going to be meters. Um, but what this equation like essentially helps us solve is that the higher that I am, right, on my skateboarding ramp, the more potential energy I have, and it also tells us because there's mass in here, the heavier I am, I'd have more stored energy because of mass is a part of this equation. But for the second type of energy that we have kinetic energy, and kinetic energy is oops. Kinetic energy is the energy that an object has as it's moving, or because it's moving. And the equation we have for this one is going to be K E equals 1 half mv to the second, where Ke is the kinetic energy with the SI units of joules, and we have the 1 half here. M is going to be the mass, and we measure that with kilograms. And V is going to be the velocity to the power of 2 up here, and that's the SI units of meters per second. And the velocity is squared because the speed is it has a huge effect on the kinetic energy in this case. So if I double my speed, then it's going to be 4 times larger. The kinetic energy is going to be 4 times larger. And that just goes to show like the kinetic energy you have when you're coming down from, like, just let's say a skateboarding ramp. And the last type of energy that we have is going to be mechanical energy. Mechanical energy. energy. Forgive my handwriting on this. Mechanical energy. And this is the total energy of just my skateboard, like while I'm riding it per se. This equation is gonna be mechanical energy equals potential energy plus kinetic energy. And if we're ignoring air resistance and friction, the mechanical energy just stays constant. But at the very top of the ramp, oops, that's not a ramp. At the very top of a ramp, right here, my potential energy is the absolute highest, while my kinetic energy is almost like absolutely zero. Right? As I'm going down the ramp, my height is decreasing because this is my height. If I'm going down the ramp, right, my height decreases only to here. Boom. My potential energy decreases, and my speed increases, and so does my kinetic energy. My kinetic energy increases, and my speed increases. The energy is not disappearing from the potential energy, it's just changing from potential energy to kinetic energy. And at the bottom of the ramp over here, I would be moving the absolute fastest with my speed the highest, and almost all my kinetic, or almost all my energy would be turned into kinetic energy. So that's just the conservation of energy explained real quickly. Now I want to solve a problem, right? And it's going to be a skateboarding problem. So let's just let's just make a new page here. I say like, okay, like I'm skateboarding at the skate park, and I'm going to be 60 kilograms. So let's make a ramp here. I'm up here on my skateboard, I'm at rest, and I'm 60 kilograms. That's my weight. And let's just say this is 5 meters high. Just keep things even. 5 meters. That's going to be the height. So the height is equal to 5 meters. My mass is equal to 60 kilograms, including the skateboard. And I'm going to be ignoring air resistance and friction, so I'm just not going to have those in here. But how fast will I be when I reach the bottom? Right here. So, okay, in this situation, I'm starting from rest. So my velocity would be 0. So that means my kinetic energy is equal to 0. So all my energy right now is going to be potential energy. So since it's all potential energy, we're going to want to use potential energy equals mass times gravity times height. And we just substitute the numbers now, nothing too crazy. So potential energy is going to be equal to 60 times 9.8 times 5. So I got the 5 meters from the height. My mass is going to be 60 kilograms, and then gravity is 9.8 meters per second squared. So in this situation, potential energy is equal to 2,940. Just check me if I'm wrong on that one. 2,940. And that SI unit is going to be joules because potential energy is in joules. So at the top of the ramp, I have 2,940 joules of stored energy up here. So because the energy is conserved, all the 2,940 joules is going to change. So my potential energy is going to change with the potential energy to kinetic energy once I reach this climax at the bottom here, or yeah, climax, I guess. So in this situation, kinetic energy is going to also equal 2,940 joules, because it's all going to get transferred to kinetic energy at one point at the bottom here, and that's what we're solving for. So now we're going to go kinetic energy, and this is just the equation, right? Kinetic energy is equal to 1/2 mass times velocity squared. We just want to substitute the numbers here. So since we know kinetic energy is 2,940 joules, because potential energy is going to get transferred to kinetic energy, this is equal to 1/2, and we already know the mass, which is 60 kilograms, which was given to us, and we're going to be solving for velocity squared in this situation. We're just going to simplify this real quickly. So this is going to be 2,940 is equal to 30 times velocity squared. We're just going to divide both sides by 30. Boom, boom. Divided by 30 is going to be 98. So 98 equals velocity squared. We're going to take the square root of both sides. Boom, this crosses out. Square root of 98 is going to be, is that right? Yeah, 9.9. So 9.9 meters per second. And we just solved. So 9.9, this is the velocity, right? So I'll reach the bottom moving at like almost 10 meters per second squared. Or not squared, sorry, 10 meters per second. And I never use time in this situation because the conservation of energy like allows us to solve problems without needing to know how long it took me to get down this ramp, which is why I like this a lot. But you know, solve for potential energy. We knew that when we got to the bottom, potential energy is going to change to kinetic energy, so we used that to find out the velocity, and this is the final answer that we got. And to elaborate further, the question I asked at the beginning, where I said, why do I speed up when I go down a skateboard ramp? Well, it's because the gravitational potential energy is just constantly changing into kinetic energy as I'm going down. And then as I go up the other side of the ramp, the kinetic energy changes back into potential energy, right? But in the real world, though, I would never make it back to exactly the same height where I started, because I am losing some because of friction, right? The friction between like the wheels and the ground with air resistance. If we're including air resistance, we are going to include air resistance. In the real world, the friction and the air resistance transforms some of my mechanical energy into back into heat. So while the total amount of energy is obviously still conserved, not all of it stays as mechanical energy. And so let's just say like this. As I'm going down, I go down and I'm back up here, right? This is potential energy peak, kinetic energy peak, back to potential energy peak. But once we go back down this way, a little bit of the pie chart will be lost, right, to friction. So this would be orange, lost to heat. So not all of it stays mechanical energy, even though the total amount of energy is going to be conserved. It's not only conservation of energy doesn't only obviously explain skateboarding. I saw that engineers use it to design like roller coasters, and divers use it when they jump off of platforms. But I feel like once you understand this concept, you start like noticing things when they speed up or slow down, or when they don't quite make it to where it was before, and you know that that's because of friction. And that's why I like this unit, and I wanted to talk about the conservation of energy. Really interesting. Think about it. Maybe you're losing speed as we speak. Maybe you're getting turned into heat.